Okay, thanks. So yes, this was a CCORN project which was run this year, and it's a collaboration between some industrial people, Howard and Yanis and myself. And with any of these kind of collaborations between industry and academia, there's a bit of a struggle because the academics want the project to produce publications and the industrialists want it to be useful. So I thought well, and I'm sure we will have some publications. Okay, so the project considers financial models, and financial models in the sense of mathematical models of things like risk analysis, of the evaluation of financial products, the underpinning financial processes such as trading and delivery of new products and so on. And the financial world is increasingly regulated as a consequence of the crisis of 2007-8 and so on. And regulators require that institutions do validate their models. So these are models somewhat in the sense of model-driven engineering, but they're heavily mathematical models. They're models of the way that the value of a product might change, or the risk associated. What is the risk associated with a portfolio that a business, that a bank has of investments? And very much driven by Howard's ideas and Howard's work, and Howard's a financial expert of decades standing. He came up with this idea of a DSL, which would combine model-driven engineering ideas and represent the financial mathematics in a natural way. So we call it MathOCL. It's underlying it is the normal OCL, which we see from UML, but it's represented with the financial notation with calculus and so on. And we built tools to support writing specifications in that DSL, to support some reasoning with the DSL specifications, and to support code generation, translation to ordinary OCL, translation to code like Java and C#. Obviously, the finance industry is a very significant industry. It hasn't taken up MDE in the same way that other sectors like avionics and the automotive sector, as we've seen already in this conference, that those sectors have been using MDE in one form or another for a long time. But it is heavily using mathematics. It's heavily using mathematical models and theories. It relies very much on precision and accuracy in those models. So it's natural to think about using MDE in this world. Definition of financial models from the Federal Reserve and the definition of model validation. Essentially, it's about building appropriate, accurate models. There's sometimes alternative ways of writing a model, alternative models you could have for a situation, and validating the models, validating that they actually perform as expected and they're fit for purpose. So MDE has been successful, as I say, in different domains, but not so much in the finance domain. There's still heavy use of tools like Excel. If people are building these models, they're more often than not using Excel. And I found myself, when I worked as a consultant in the sector, that notations like OCL, it was like the kiss of death. Basically, people didn't want to invest the effort to understand what to them would be an arcane notation. So we really have to focus on domain-specific constructs and to go to the user and essentially say, well, what notation do you want to work in? What do you find natural to work in? The answer essentially is mathematical notation. So these are often mathematical, they have mathematical PhDs. They have PhDs in mathematics. They're very clever people building these mathematical models. They're not necessarily programmers, but they do know a great deal of the mathematical theory that needs to be used for these models. Also in this, not only calculus, but also stochastic. You have stochastic differential equations. You have stochastic models based on different kinds of random variables, like the normal distribution. To reason about these models, you need to do algebraic simplification, symbolic evaluation of differentials, for example, some kind of reasoning. And the idea we wanted was to be able to have a language and a tool in which you could do lots of these tasks in a kind of seamless way. Obviously, there are lots of tools out there like PySim, like Isabelle. There are various tools for doing algebraic simplification and proof. But we didn't want people to have to switch from one tool to another using translations. We'd like really to have a seamless thing within one interface. This is what the industrialists are telling us. This is what Howard is telling, Howard and Yanis are telling us. So, I tried my best to do this. It is a huge job, and we only had 3 months, so it's only really just a starting point, what we've done. We defined a grammar for this math OCL. We have a specialized tool, which is itself a DSL, but it's a text-to-text modeling transformational language, model transformational language. It goes text to text, concrete syntax to concrete syntax. And I found, much to my surprise, that this could be used in a recursive way. I was thinking of it as a single shot from one language to another. We're doing, for example, UML to Swift, or we were doing COBOL to UML, single shot. But here we were using it as a recurrently to do algebraic simplification, which was surprisingly effective. You can also break that cycle to do interactive editing. So here's what the interface looks like. I can write a simple little model here, a variable x that follows an normal distribution. I want to evaluate what its expectation of 2 times x is, and so that's what the user writes, and then they get the analysis here. Now they can then edit this if they want to change the result. They want to do some further simplification analysis, do some deduction. They can edit at that level as well. Limits, evaluating limits. We have a couple of PhD students working in the area, and one of them is a guy from insurance. He actually works at an insurance company. He's doing a part-time PhD, and they do things like life insurance equations, differential equations to estimate what benefits you get at different stages of your life if you've got investment life insurance and so on. So Thiel's equation, it's a real kind of system. And then another case study was a detailed evaluation of bond pricing using actual practices, not simplified academic solutions, but using actual practices. So this is a real model. This is the Thiel's equations, the specification. This is the automatic solution of it using rules for solving differential equations. That's not trivial. And then here we have the OCL equivalent of it. This OCL equivalent then is directly translatable into languages like Java and C#. Similarly, here's the bond pricing one, specification, simplification, there's not much difference in that case, and then translation to OCL, which would give you to then translation to code. That's more detail of another case study. So top model gives a mathematical notation, which that's what the user would typically write. And then we do some syntax checking, guidance, some algebraic simplification solution where possible. That can be done interactively as well. And the solution in the lower panel, and then on the right-hand side, the OCL. There's another solution. We're adding more in the way of proof construction and theorem proving. That's obviously a big area. Some simple proof checking can be done already. There's an example of proof. It solved some of those automatically, but some still remain. Then generation of code. From those simplified and explicit math OCL specifications, we can go to OCL, and from OCL then to whatever language, really. We also want to link to the ZUp Dev. There's a low-code platform that Yanis's company is supporting. So we link, as well as generating OCL, we can generate Mamba 3 in their language for the ZUp Dev. And that also then gives links to C# and all sorts of web and mobile and every other kind of thing. Here's some code, C# code from the Thiele's equation. It's too small to see, I'm afraid. And some C# code from another of the problems. And we also, well, mainly me, I built these libraries, OCL libraries for mathematics, for dates, and for specialized financial solutions, and those, those being maintained as we go forward. They support the implementations. Okay, so there's been quite a lot of work in this field, mainly though at a theoretical level. One of the more practical aspects was the capital system, but now that doesn't seem to have gone forwards. Where we think MathOCL is novel is that it includes modeling of financial processes, not just a kind of static specification, but it shows these dynamic aspects of a system. And it also uses, where possible, conventional mathematical notation rather than some program-like syntax, because these users, as I say, they have their expertise very much in mathematics. Okay, so I think the project achieved quite a lot. We did manage to do 2 realistic case studies to complete these case studies as demonstration examples, and we have prototype tools which show at least that the idea is feasible. Of course, there's a lot of work that can be done, and we are planning to put forward more proposals to give a substantial development in the future.
Thank you very much.